just about at the end of this group of topics, which has pretty much all been about lines, if you had noticed. The important part, or at least I would say the most important parts, were the sections on slopes and equations of lines. You're going to see that a lot. You're going to use it a lot. This section, this video won't be as long as the last two, I don't think. These results are fairly simple and, almost obvious. For instance, this one. Two lines intersect to form a linear pair of congruent angles, and the lines are perpendicular. Now, let's just break this up here. They form a linear pair. That means that they add up to a straight angle. Linear pairs add up to 180 degrees. These angles are congruent, which means their measure is equal. So we can just pick one. Let's say the measure of angle 1. And multiply it by 2. And that has to equal 180. Why? Because we'd write angle 1, measure of angle 1 plus the measure of angle 2 equals 180. Since they're both equal, we just substitute either one. We could have written 2 times the measure of angle 2 equals 180. Either way, we get that angle 1 equals 90 equals the measure of angle 2. See? Very simple. I bet if somebody asked you, told you these two angles are equal and that's a straight line, what do you think? I think you would probably, without doing any equations at all in your head, realize that these are both 90-degree angles and G is perpendicular to H. Down here, let's see here. If two lines are perpendicular, then they intersect to form four right angles. Wow, that's almost a definition of perpendicular. But again, I don't think you'd have any trouble spotting the truth of this. It's pretty simple, isn't it? What would you expect to happen? These two are pretty much exactly what you'd expect. So they're pretty easy to remember. In fact, they didn't even bother to give these 3 names. They're just theorems. It's just the theorem that says this stuff. The theorem that says this stuff. Some more important theorems have names, like down here. The theorem that you can't see the rest of, but only the name. You'll see it in a minute. There's one cool thing about this section, though. There are no postulates, only theorems. Minimizing the number of postulates is always good. I don't know why. I just think it's good. Yep, no postulates, just theorems. And about down here. They say that BA is perpendicular to BC, then angle 1 and angle 2 are complementary. Well, again, that's almost the definition, not quite. But if you see something broken up like this, and this is the right angle, then these two are complementary. Again, that's real easy. Your instructor is probably having you prove these in class. Since you've seen these nice, simple proofs, I'm not going to duplicate it. There's a couple more theorems, and then we're just going to do the problems because, well, actually, a couple more. These are all very intuitive. I don't think you'll have any trouble remembering these. Transversal is perpendicular. Well, let's read this one down here. If H is parallel to K and J is perpendicular to H, then J is perpendicular to K. What the heck's all that mean? Well, down here. H and K are parallel. J is perpendicular to H, then it's also perpendicular to K. And it is it's called the perpendicular transversal theorem. It's kind of like a transitive property, isn't it? Again, we're just passing right through. We're saying if this line forms a 90-degree angle with this line, and this line is parallel with this one, then it must form 90 degrees here also. It's kind of like the transitive property. It's perpendicular to this line, so it must be perpendicular to this line too, because it's parallel. What about this? Well, this is kind of similar to the converse, I would say. But not quite. We haven't perfectly reversed these, but real close. If M is perpendicular to P, and N is perpendicular to P, in other words, they're both perpendicular to the same line, then they must be parallel to each other. Here, they're both parallel. If one line's perpendicular to one of them, then it's perpendicular to the other. Here, not exactly the converse, but it's close. This one says that if the transversal cuts them both perpendicular, then they are parallel. And that's kind of simple, because we already know that if from our corresponding angles theorem, that if these two angles are congruent, these two lines are parallel. So this is just a special case, really. You get that a lot in mathematics. They're called special cases. It's just a broader theorem which is narrowed down to only apply to one little small case, in this case the right angles. The broader theorem is the corresponding angles theorem. In fact, in the world of mathematics, something like this is frequently called a corollary. You probably don't need to know that, but if it comes up, a corollary is kind of like a mini theorem. It's a Mach theorem. Or is it Mach theorem? Yeah, Mach theorem, I think, is what you would say. It's something that follows pretty directly and easily from some other theorem, so it's called a corollary to that theorem. There's no hard and fast rule for setting the line between theorem and corollary. It's kind of subjective. The most important thing, I believe, in this section is a simple little thing called distance from a point to a line. What is the distance from a point to a line? Now there's a point, and there's the line. Well, gee, that could be a distance. That could be a distance. We could go, well, maybe we want to take the river route back to the line. None of these would actually be defined as the distance from the point to the line. What would be? Well, if I can draw it, it would be a line from the point perpendicular to the given line. Why do we pick that one? Well, for one thing, we got to pick something. For another, that is the shortest distance from the point to the line. It has that unique property, and since it is unique, in fact, we can define, if we want to reverse it, a more sophisticated math class, we could define, well, say the length of a segment which connects this point to this line, define it to be the shortest distance from the point to the line, and that will turn out to be a line passing through the point and perpendicular to the given line. So the perpendicular distance is what it's frequently called. It's also used in determining the distance between two lines. For instance, what's the distance between this line and this line? Well, right right here it's 0. Up here it's quite a bit more. We don't have a definition right now for the distance between these two lines, because after all, they're lines. These continue off that way. This one, in theory, continues off that way. Well, where do we define the distance? It just takes off to infinity, and that takes off to infinity. Then at some point they are infinitely far apart. I guess that would follow, but it's kind of hard to work with. So how do we define distance between lines? Well, we don't unless they're parallel. Parallel lines have distance between them. So now we can define distance. And is it this distance? Or is it that distance? No. It is the perpendicular distance between the two parallel lines. That is the distance between the two lines. Okay, now we've got a world of information about perpendicular lines. Let's work a few problems. Now we have some of those cool find the error problems. What we have here is some dopey guy who makes geometry videos. The scientific abbreviation of that is SDG for some dopey guy. So we've got an SDG who thinks that these lines, Y and Z, are parallel. Well, this is perpendicular. What about over here? Well, it doesn't say explicitly that it is perpendicular, and we can't just assume that it is. Even though this line looks parallel to this line, you can't go by that. Unless you're extremely good, say a 1 degree difference here, probably wouldn't be noticeable. So we'd have to have our little red square right here, and then we could say that they were parallel. But no, as it is, it would be wrong to draw this conclusion. The diagram doesn't support that conclusion. Now this one, once again, that's incorrect. We have to draw a perpendicular line here. I'll just draw it in dots so that this forms a right angle. Then this distance here, and this distance will definitely be less than 12 centimeters. Remember, I mentioned earlier that it also turns out that the way we define the distance from a point to the line is the shortest distance from the point to the line also. So, you see what the errors are here. Here, he just assumed this was a right angle, but we don't know that it is. Here, I don't know what the assumption was. It's just a mistake. It's just, why pick that line? You could draw a line out here and say that's the distance, and you could draw it out there. No, the shortest distance from the point to the line, which is the perpendicular from the line to the point, that's the distance we use. Now here we have another easy one. We're using perpendicularity right here. Line FG, that's that one, is perpendicular to line GH. That's given. We don't have to assume it. So perpendicular means it's a right angle, so we can draw that in if we wanted to. We don't need to. We know that these are perpendicular, which means this is a 90-degree angle. This part's 20 degrees. So once again, we just set up our algebraic equation. 20 plus this has to equal 90 degrees. Plus x minus 25. So these two add up to a minus 5. We add 5 to each side and get that. And we get that x equals 95. The fact that x is greater than 90 seems odd, but we're subtracting 25 from it here. So if we do that, we should get 70. And 70 and 20 is 90. So there we are, all done. All we had to do was recognize this is 90 degrees, and then set up our old friend, the algebraic equation. Now, if we assume, which the statement here says, if C is perpendicular to D, if that's true, which one of these must be true? Well, m1 plus m2 is less than 90 degrees. Gee, I don't think so. I mean, perpendicular means that they intersect at right angles. Right angles are 90 degrees. And these two add up to this. Or you could say these are congruent. I just said congruent. Of course, I meant complementary. Angles. So less than 90? No, I wouldn't say that. Greater than 90? I wouldn't say that. Cannot be determined? Well, sure we can determine it. In fact, they add up to the whole, which is 90 degrees. So you probably, before I even started talking, you probably immediately looked at A and said, well, that's the answer. Just be quiet. Okay. Okay, here we're going to use a lot of what we know about angles, and it's also going to be real easy. Really. Honest. Let's start with this one here. We know this, right? Well, we've got this line and this line crossing, which means angle 3 and this angle form a vertical pair. So angle 3 must also be 30 degrees. Now, it's really tempting to say angle 2 must be 40 degrees. Well, wait a minute. We've got this line and this line. This doesn't continue up that way. This kind of looks like the opposite angle from that, but it's not. This angle plus angle 4 would be opposite to this. So we've got to do a little more work. However, what do we have here? Straight line. So angle 1 and then the other angle, which combines angle 2 plus this 30-degree angle here, they each form right angles. We've got the right angle over here, and let's see here, I think we've got a theorem up here. This might be the theorem to use. If A is perpendicular to B, then all these are right angles. So this is a right angle, these two are perpendicular, so they're all right angles. And more importantly, right now, this is a right angle. If this is 30, then this must be 60. But now we have that these two angles together, this, in other words, this angle here and this angle here, they form a vertical pair. If this is 60, then this larger one must be 60. But it is from our angle addition postulate, the sum of 40 plus 4, and that equals 60. Do we even need to do the algebra to figure out that this one must be 20 degrees? 40 plus 20 is 60, same as this one here. Okay, now this, from our 4 right angles theorem up above there, this is 90. And this, well, gee whiz, they put it right here. That's automatically, that's 90. So, there's every angle, which we found by using vertical pairs, our angle addition postulates, and properties of right angles. Again, actually very simple, I think. I don't think you'd have any trouble with all doing this. Most important part probably was just spotting the vertical pairs and not getting confused and accidentally thinking that this and this one here form a vertical pair. It's this and these two together form the vertical pair. Other than that, it seemed like a pretty easy problem. Here's one where we apply our properties of finding distances between lines. Remember, it's the perpendicular distance between the two lines, and we can only find distances between lines if they are parallel. Are these lines parallel? Well, let's see here. Remember, if lines are parallel, they have the same slope. So maybe I should just rewrite this one in our slope-intercept form, so they both have the same format. So we got 2y equals minus 1 plus 3x. So y equals 3 over 2x minus 1/2. Now let's see, we have a slope of 3 halves here, and a slope of 3 halves here. So they are parallel. So we're not spinning our wheels if we try to find the distance. We can actually do it. It would have been kind of nasty, but they could have given us two lines that weren't parallel, and we'd just be sitting here totally confused trying to figure out what it is they expect us to do, because you can't do that. But we verified it anyway. These two lines are parallel. Now, I'll show you something really easy here. Suppose we got two lines, and this is not intended to be a graph of the lines in question, okay? Let's say that they're parallel. Wow. Like I said, let's say that they're parallel. They may not look parallel, but take my word for it. Gee whiz. There we go. You didn't see that part. That doesn't count. We've got a y-axis here and an x-axis here. And we've got these two parallel lines. What's the distance between them? We have to take the perpendicular distance here. So it'd be really nice if we could just take this and find the distance between the two y-coordinates, but can't do that. That's not the perpendicular distance, is it? If we happen to have straight lines here, we could do that, but that's a shame. Sure would be easy, wouldn't it? So we'll have to do it in a different way. This is the distance we actually have to find here. The first thing we need is a line perpendicular to these two lines. Which line? Well, it doesn't matter, does it? However we draw lines between these two parallel lines, as long as it's perpendicular, we will get the same answer. So what would the equation of a line perpendicular to these two lines be? Well, there are an infinite number of them. So let's grab the simplest one. Y equals minus 2/3 x. Why? Well, I use that. Remember, the slope of a perpendicular line is the negative reciprocal of the slope of the original line. So if we want a line perpendicular to a line with this slope, it has to have slope minus 2/3. As far as the y-intercept, it doesn't matter. So I just kind of sketched that in right here. I didn't kind of sketch it in, I did sketch it in. I wonder if Alexa could recognize that phrase. I could maybe program Alexa to smack me upside the head every time I say kind of. That would break me of the habit. Does Alexa have arms? I guess I'd have to rig up some electronic thing and give me a shock, I suppose. Well, now that I've solved that problem, let's get back to this one. Y equals minus 2/3 x is this straight line here. So all we need to do now is find the distance between this point and this point. But what is this point and this point? Well, remember the last section we worked out what the intersection of two lines would be? They're either parallel and they don't intersect. They're the same line and they have an infinite number of common solutions. Or they're like most lines. They intersect at exactly one point and they have one unique solution. These lines intersect, so we have one solution. All we need to do, for instance, to find say the point where this line and this line intersect, is set them equal. So we just write 3/2 x plus 4 equals minus 2/3 x. So to find our intersection points, as I said, we'll have to set this equation equal to this, and then set this equation equal to this after we've put it into this form here. Kind of messy, isn't it? And that's only the beginning, because once we've got our points, our intersection points, then we have to use our distance formula and find the distance between them. It's pretty long calculations. I went ahead and wrote it out so you'd have to sit there and watch me do all this writing. We set this up. 2/3 x plus 4 equals this line over here. Let me just set them equal in order to find out this point that satisfies both equations. So we lay out the equation, add 2/3 to each side, do the arithmetic here, and you get 13/6 times x equals -4, or x equals -24/13. That gives us our x-coordinate over here. Well, that's one good step. What about our y-coordinate? Well, we just put that back into our equation for the line. Now remember, this point has to satisfy both lines. So we can use either line to find the y-coordinate. We could put x back into here, or we could put x back into this one here. This one looks easier to me. So that's what I did. I took the x that I got, plugged it into this one, and got this for our y-coordinate, 16/13. So, one of our intersection points is -24/13, 16/13. And remember, we arrived at that by setting the equation for this line equal to the equation for this line. We solved for x. Once we got x, we put it back into either equation to get our y-coordinate, and now we have an intersection point. And then we're going to do that again. Same thing, but with our new formula up here. This is the other line, which we rewrite into our slope-intercept form and get this, and use it down here. Now we set this, in a sense we're setting this equation for this line equal to the equation for this line, which will give us our other intersection point. We do a whole bunch of algebra, and in a very similar way, we get that x equals 3/13. How do we do that? Well, we added 2/3 x to each side, and that gave us 13/6. Put the 1/2 over here, so we got 13/6 x equals 1/2. And then we just solve 6/13 times 1/2 is 3/13. We put that into our simple equation for the perpendicular line, and we get -2/13 for our y-coordinate. So there's P2, 3/13, -2/13. Now we have these 2 points. What do? We apply our distance formula. What's the distance from point P1 to P2? And if you're upset by the fact that we're not working with any pictures, don't worry. I've got a graph all laid out, and we're going to show it to you in a minute. But I wanted you to see that you don't actually have to have a picture other than that, that simple little thing I drew right here, just to give me an idea what I was working with. But even that was unnecessary. It really forms no part of the solution. We did it all just using algebra so far. And in fact, we can answer the entire question using nothing but algebra. But the graph is a good way to see if our answer makes any sense. So we've got P1, put it so you can see it there. We've got P1 and P2. So we just use our distance formula. In this case, x1 minus x2. Really doesn't matter which order you subtract these in, because we're going to square it. If you reverse the order, you'll get a negative number here, but after you square it, it'll become positive again. So for the distance formula, you could mess up the order a bit, and you'll still get the right answer. That's cool. And over here, we've got our y1 minus y2. Now what I did was I factored out the 13. Got 13 here and 13 here. We could factor it out, it would be squared. And we put it way out in the front here, and we'd have 1/13 squared. And then we could pull it out here and be 1/13, and that's what I did. think you're familiar with this from Algebra 1. So it's 1 over 13 times the square root of this stuff. Minus 24, minus 3, that's minus 27. Pardon me, 16 minus a minus 2 is 18. And we're going to square it and take the square root. This number here is like 1035, I think. I forget what the square root of that is, and when we divide by 13, we get 2.5 as our distance between the two lines. Does that make any sense? Well, let's take a look. Well, here we have a graph of the situation. Here's our line, 2/3 x plus 4. And here's the other one, which after we put it into our explicit, that's another name for that slope-intercept form, when you've got y on one side and everything else on the other. It's also called explicit. And after we rewrote it into our y equals 3/2 x minus 1/2, we get this line. And minus 3/2 x, that's this line perpendicular here. We got 2.5. And that looks about right. I mean, the distance from here to here is about 2.5. That's a bit off, but at least we're in the ballpark. I mean, if we got 5 or 1.3, we'd know we were wrong. The 2.5 looks about right. In fact, if you had a ruler or something and held it up to the screen and then laid it down here, you could see that 2.5 makes perfect sense. What did we get? Well, let's see here. I was going to say, when we computed our intersection points, minus 1.8 is in fact what you would get if you took minus 24 over 13. And 1.217, that's what you would get with the and 16 over 13 is about 1.23. So we got our intersection point right here. And up here, let's see what we get. Close. Yeah, remember we had like 3 over 16 and minus 2, or pardon me, 3 over 13 and minus 2 over 13. And let's see, if you use your calculator or do a little long division, you'll find that that's the decimal representation of those two fractions. So we got our intersection points right. Our distance that we derived actually makes sense, so we might have actually gotten the right answer, huh? Well, just remember that one of the most important things about perpendicular lines in this class is going to be that finding distances from points to lines. It's very important to understand that you're talking about a perpendicular distance from a line to a point. The next video will just be a review